When safety practitioners assess a construction site, the instinct is to look up. Extreme heights draw our attention because the potential for a catastrophic fall is obvious. But to understand the true distribution of risk, we must examine the data at ground level, starting with a baseline height of exactly 2 meters. This chart shows the statistical reality of workplace falls. Below that 2-meter line is where 60% of all major injuries from height occur. The highest volume of severe trauma happens at elevations barely taller than the workers themselves. The data shows a massive concentration of major fractures in this specific zone. At lower altitudes, workers frequently skip safety precautions. Complacency and a false sense of security lead to a high volume of severe injuries that could have been entirely prevented. Vertical distance is only one component of the risk matrix. The danger of a fall is multiplied by extrinsic variables, such as the sudden failure of fragile roofing materials or unexpected changes in weather conditions. Severe risk at height does not scale in a straight, linear line with altitude. Recognizing this statistical anomaly requires site managers to apply the exact same rigorous safety standards to a low-level trestle as they would to the top tier of a tower scaffold. The Working at Height Regulations 2005, or WAR, removes any ambiguity about what constitutes an elevation risk. Under the law, work at height is defined as work in any place, above, at, or below ground level, where a person could be injured falling. This means a worker standing entirely flat-footed on the ground is legally working at height if positioned adjacent to an open, unprotected excavation trench. Furthermore, the regulations strictly stipulate that the access and egress routes leading to these working positions are equally classified as work at height and require identical risk assessments. This diagram outlines the WAR hierarchy of control. It cascades through 3 mandatory steps: avoid, prevent, and minimize. This is a legally mandated sequence of failure. You cannot move to a lower tier unless you prove the tier above is impossible. Within the prevent and minimize tiers, there is a strict internal rule. Collective protection, methods that secure everyone in the area without relying on individual action, must be exhausted before personal protection equipment is even considered. A site manager cannot simply hand out personal fall arrest harnesses. Doing so requires documented proof to an inspector that engineering a collective preventative measure was entirely unachievable. Step 1 of the hierarchy is avoidance. The optimal control measure is to eliminate the elevation hazard entirely by engineering the work at height out of the project during the design stage. We see this in practice when contractors assemble complex, heavy steelwork at ground level and crane the completed structure into place, or when maintenance teams utilize ladderless extension poles to clean windows from the pavement. When avoidance is impossible, we drop to step 2, prevent falls, specifically using collective measures. This requires the construction of stable working platforms. This diagram illustrates an independent tied scaffold. It is built using 2 parallel rows of vertical tubes, known as standards, which support the deck. Because it stands independently from the building face, it relies heavily on precisely spaced anchor ties drilled directly into the structure to maintain stability. By contrast, a put-log scaffold eliminates the inner row of standards. Instead, it uses flattened horizontal tubes, the put-logs, which are lodged directly into the mortar joints of the brickwork to support the inner edge of the working platform. Regardless of the scaffold type, edge protection regulations are exacting. A compliant platform requires a main guardrail at a minimum height of 950 millimeters, an intermediate rail to close the gap, and solid toe boards at least 150 millimeters high. These temporary structures are highly regulated and must comply with exact structural specifications, specifically BS EN 12811-1 and TG 2013, which is the UK industry's technical guidance for tube and fitting scaffolding. A fully compliant scaffold physically engineers the risk of a fall out of the environment. It delivers a safe place of work, fulfilling the legal mandate for collective prevention. When static scaffolding is not viable, site managers turn to mobile elevating work platforms, or MEWEPs. These maintain the standard of collective prevention while honoring mobility. MEWEPs come in distinct variations. Scissor lifts provide a highly stable, vertically operating platform. Articulated telescopic booms, on the other hand, use a jointed arm to deliver height, extensive lateral reach, and platform maneuverability. MEWIPs also have strict environmental operating limits. Manufacturers generally prohibit operating these platforms in wind speeds exceeding 28 miles per hour, as lateral force can easily overturn the extended structure. Operators must also avoid any shock loading. Shock loading is a sudden, destabilizing force applied to the platform equipment, typically caused by erratic, jerky control movements or by an operator dangerously jumping from an adjacent structure back into the basket.
If collective prevention via platforms or MEWIPs cannot be achieved, we move to step 3 of the hierarchy: prevent falls using personal protection. The primary tool here is a work restraint system. This diagram shows the geometry of work restraint. The lanyard connects the worker's harness to a fixed anchor point. The length of this lanyard is measured precisely so that the worker is physically prevented from ever reaching the unprotected edge of the roof. The mechanical application changes, but the objective remains identical to scaffolding, keeping the worker confined within a defined geometric boundary where a fall is physically impossible. When prevention measures are exhausted, the hierarchy forces us to step 4, minimize distance and consequences. If you cannot prevent the fall, the system must be engineered to catch the worker. Safety nets are the collective standard for this tier. Compliant with BS EN 1263-1, they must be erected by competent riggers and installed as close to the platform as physically possible to limit the kinetic energy of the drop. Alternatively, inflatable airbags provide rapid deployment directly beneath the work area. They deliver a soft landing with minimal rebound, completely isolating the falling worker from the solid ground below. Moving further down brings us to step 5, minimize using personal protection. This is the domain of fall arrest harnesses. This vertical diagram details the exact mathematics required for fall arrest. You must calculate the length of the lanyard, plus the shock absorber deployment distance, plus the worker's height, plus a safety margin. If this combined total exceeds the distance to the ground, the system will fail to prevent a fatal impact. Finally, at step 6, we reach ladders. The WAHR classifies ladders strictly as a last resort, legally permissible only for light, short-duration work where establishing a safer platform is unjustified. When a ladder is used, it must adhere to an absolute geometric rule. For every 4 units of vertical height, the base must be placed 1 unit away from the wall. The ladder must then be securely tied off at the top or footed by a second worker at the base. Relying on fall arrest systems or ladders is an admission of failure. It places the worker at the edge of allowable legal risk. The hazard assessment must extend beyond the engineered platform to the surface of the structure itself. Fragile roofing materials act as massive risk multipliers. Lightweight asbestos cement or brittle perspex roof lights are rarely designed to bear human weight. Years of environmental weathering, dirt, and moss growth camouflage these critical weak spots, making them indistinguishable from solid roofing. Navigating these surfaces require mandatory controls, deploying adequately supported crawling boards to distribute weight, and erecting prominent warning signage at all approach points. The secondary hazard of working at height is the dropping payload. Site managers have a legal duty to protect third parties, contractors, and the general public from objects falling from the work zone. This containment starts at the platform level. Scaffolds must be fitted with solid brick guards and fine debris netting to trap loose materials, grit, and tools before they can breach the edge. This diagram details a protective fan. These angled structures extend outward from the building facade, specifically to physically intercept falling bricks or aggregate, shielding pedestrian routes below. They are categorized from Class A to Class D, depending on their required load-bearing capacity. At ground level, the Construction Head Protection Regulations 1989 dictate strict enforcement. Hard hat zones must be clearly designated and mandatory for all workers and visitors exposed to overhead risks. A system of work at height is legally incomplete if it only focuses on the worker's balance. It must contain the devastating kinetic energy of dropped objects. When preparing for a NEBOSH assessment, one critical requirement is frequently overlooked by candidates: the emergency rescue plan. A site cannot legally rely on simply calling the emergency services if a worker falls. Immediate, pre-planned recovery equipment and trained personnel must be stationed on site before the work begins. This chart illustrates suspension trauma. If a worker is left hanging motionless in a fall arrest harness, gravity causes blood to pool rapidly in the lower extremities. This restricts oxygen to the brain and can quickly become fatal, making immediate recovery critical. Rescue methodology dictates that lowering a remote casualty to the ground is always physically easier, faster, and safer than attempting to hoist them upward over an abrasive edge. One of the most effective pre-planned strategies is the immediate deployment of an on-site MEWEB to intercept the suspended casualty and bring them to safety. For the NEBOSH examiner, competence is proven through strict sequencing. You must map the exact hazard, identify extrinsic multipliers like weather or roof fragility, and apply the WAHR hierarchy without skipping a single step. True mastery of Element 7 requires engineering a tripartite system. You prevent the worker's fall, you catch the dropped payload, and you guarantee an immediate rescue.